Okay, we're going to do this example, solving problems using conservation of mechanical energy, and we're going to use this example from the notebook, which is this roller coaster example. And so one question that you might encounter when doing these types of problems is, what is the velocity of the roller coaster at position 1 and position 2? Okay. Now, before we even answer this question, let's look at the roller coaster. And just from your experience, can somebody tell me, is the velocity greater at position 1 than it is at position 0? Okay, so one answer is the velocity is constant. The other answer is the velocity is greater. Okay, yeah, so as you go downhill, your velocity increases. Therefore, what type of energy increases? The kinetic energy increases. If conservation of mechanical energy is true, and the sum of potential plus kinetic is constant, but your kinetic energy goes up, what has to happen to your potential energy? It goes down. So as you go downhill, your potential energy goes down, your kinetic energy goes up. As you go back up the next hill, what happens to your kinetic energy? It goes down. And your potential energy goes up. In fact, the difference between the two potential energies at 0 and 1 is equal to the gain in kinetic energy. So that's kind of the way we're going to solve this problem. Okay. I want you to use the guess method when you solve these problems. So the first thing we're going to do, we've drawn a picture already. We're going to write down our givens. We were given that the mass is 1,000 kilograms. And the height at position 0 is 20 meters. The height at position 1 is 5 meters, and the height at position 2 is 10 meters. Also, we were told that the initial velocity of the roller coaster, V0, is 0 meters per second. I'm going to show you a way that you don't have to have the initial velocity 0. As long as you know what the initial velocity is, you can still solve the problems. Okay, our unknown, we want to know what is V1 and what is V2. The velocity at position 1 and the velocity at position 2. Okay, our equation that we're going to use is the conservation of mechanical energy. So the big equation, the overall equation really is just mechanical energy at 0, position 0, equals the mechanical energy at position 1, and that equals the mechanical energy at position 2. Okay? Now, we can substitute our definition of what mechanical energy is into this equation. Mechanical energy at any position is just the sum of all the different energies that are mechanical energy. So gravitational potential plus kinetic, and even you can solve problems using elastic potential energy. Now, in this particular problem, we have no elastic potential energy, so I'm not going to even include this when I solve the problem. Now, we can take this a step further. These are equal to mgh plus 1/2 mv squared plus 1/2 kx squared. That's gravitational potential plus kinetic plus elastic potential. Again, I'm not going to use elastic potential because it's 0. Okay, so let's rewrite this equation in terms of these. It's kind of a long equation, but you're going to see it's just algebra once you get the equation. Okay, so for position 0, we have mgh0 plus 1/2 mv0 squared. For position 1, we have mgh1 plus 1/2 mv1 squared. Okay, I'm going to stop there, and I'm going to solve for the velocity at position 1. So I'm going to substitute values. This represents the energy at position 0. It has to be equal to the energy at position 1. So the mass, 1,000 kilograms, times gravity, which is usually given, it's 9.8 meters per second squared, times the height, which is 20 meters, plus 1/2 times the mass, 1,000 kilograms, times the velocity at position 1 squared. That's the energy, mechanical energy at position 0. It's constant, right? It doesn't change. So this is this part here. We can go ahead and calculate this out, but I'm going to go ahead and write this part. All of this, I'm going to put the equal sign down here so I have enough room, equals this, which is 1,000 kilograms times 9.8 meters per second squared times the height at position 1, which is 5, plus 1/2 times 1,000 kilograms times the velocity at position 1 squared. We don't know what that is, so we're going to leave the variable. Okay, we're going to take it down a step. I'm going to skip a step, or skip a space, and I have 1,000 times 9.8 is 9,800 times 20. 196,000, I think, is what it is. Joules. Okay. Now, what does this equal? We have equals, and then we have 1,000 times 9.8 times 5. 49,000. And that's joules. Notice, it's kilogram meters squared, because you have m times m, meters squared per second squared. That's a joule. Plus 1/2 times 1,000, 500. 500 kilogram times V1 squared. Okay, using our algebra, we need to get all the numbers over here on the left-hand side. The first step, it's basically the reverse order of operations, right? So in reverse, the order of operations would be subtraction and addition first, if you're reversing the order. So we're going to reverse, and we're going to subtract 49 from both sides. So you have 196 minus 49 is 147 joules equals 500 kilograms times V1 squared.
And just to get a good understanding, 196 came from the first part, right?
Yeah, 196,000 is the product of these three numbers.
Yeah. And 49,000 is the product of the second one.
Say that again.
49,000.
49 is the product of these three numbers. This is the amount of potential energy at position 1. This is the amount of potential energy at position 0. So we're going to subtract 49 from both sides, and you get 147, which is the difference between the potential energy at position 0 and position 1. Now, to get V1 squared by itself, divide by 500. See, 500 is being multiplied by V1 squared, so we have to do the opposite order of operations. We got to divide because we're multiplying. So we're going to divide by 500 kilograms on both sides. And you got 294. Now, if you divide a joule by a kilogram, you get a meter squared per second squared. Because a joule is a kilogram meter squared per second squared. That's what a joule is. So if you divide by kilograms, it cancels this kilogram out and you end up with this. This is equal to V1 squared. Now, how do you get V1 by itself? Take the square root of both sides. And we get that V1 is equal to 17.15. And the square root of meter squared per second squared is meters per second. Okay? All right, so we've solved for position 1. And now we can solve for position 2. Nope, we solved for velocity at position 1. That's it. Okay? So now what we do is, we already know what the total energy of the system is. It's 196,000 joules. The conservation of mechanical energy says that the mechanical energy at 0 is equal to the mechanical energy at 2. So you don't have to redo this part. This is 196,000. That is going to be equal to, if you look at this, it's going to be equal to the potential energy at H2 plus the kinetic energy at position 2. So set your new formula, mgh0 plus 1/2 mv0 squared equals mgh2 plus 1/2 mv2 squared. And then you repeat the process. So let's do that. I'm going to substitute. I already know that this value is 196,000. I'm not going to recalculate that. And that's equal to 1,000 kilograms times 9.8 meters per second squared times the height, which is 10 meters, plus 1/2 times the mass times the velocity at position 2 squared. So we got 196,000 is going to be equal to 98,000 joules plus 1/2 times 1,000 is 500. That's a plus sign there. Plus 500 kilograms times V2 squared. Next step, what do? Subtract 98 from both sides, and you get 98. Thousand joules is equal to 500 kilograms times V2 squared. Then again, we're going to use algebra. How do we get the 500 over to the other side? Divide both sides by 500.
These guys, they used to be physics teachers.
Mm-hmm.
They rap now and they be showing examples. They call them mini game quiz.
Oh, yeah?
Yeah. It's a video called the Whisper Song.
I'm going to have to watch it. And then get V2 by itself. Take the square root of both sides, and you get V2 equals 14 meters per second. Okay.